Hi everyone, welcome back. This is lecture 4-11, and we are going to wrap up the chapter 13 outline with this video. So in this video, we're going to be talking more about acids and bases, and specifically we'll be talking about sort of the quantitative aspects of it. And we're going to start off where we left the last time, which is section 3, strong versus weak acids and bases. So you might recall that I presented this table with what we're calling the 6 strong acids. So we're going to assume that these are the strong acids and that every other acid, no matter what it is a weak acid. Now we need to talk about what it means for an acid to be strong or weak, and also for bases. So let's get into that first. What makes these acids strong and the others weak? So because we've already talked about electrolytes, it's actually really easy for us to understand what is meant by the term strong or weak acid. So it turns out that a strong acid is defined as a strong electrolyte. And what that means is that strong acids, just like strong electrolytes, ionize 100% in aqueous solutions. Here's an example with sulfuric acid. If we put sulfuric acid into water, it ionizes into 2 protons and a sulfate anion. Now, when it ionizes 100%. So there's no more H2SO4. It's all in the form 2 H pluses and 1 sulfate. So it's completely ionized. Now, on the other hand, weak acids are weak electrolytes. And what that means is that weak acids, just like weak electrolytes, only partially ionize in aqueous solutions. For example, acetic acid. When it's dissolved in water, it does ionize to a certain extent into a proton and an acetate anion. Now, when it ionizes, there are still like 90% of the acetic acid molecules in their whole unionized form, and only about 10% of it is actually ionized as the proton and acetate. So this makes acetic acid a weak acid and a weak electrolyte. So that defines the difference between a strong acid and a weak acid. It's entirely based on their ionization in water. It's either complete ionization or somehow a partial ionization. Let's go to the next page and let's talk also about the strength of bases. So just like with acids, we also can define the strength of a base. And a strong base for our purposes, for this class, is going to be limited to those materials that can generate hydroxide in solution. We're going to stick to Arrhenius's definition for a base. So basically what we're going to say is that a strong base is any ionic compound. That's something that can ionize. So it consists of a metal and a nonmetal. So it's any ionic compound that when it dissolves in water, hydroxide ion is produced. So that would be any metal hydroxide. So sodium hydroxide, potassium hydroxide, lithium hydroxide, really anything that is a metal and a hydroxide. And for strength and weakness, let's just assume that all of these metal hydroxides are strong bases, which is actually true. And let's limit our scope for weak bases to be just one thing. Let's consider ammonia. Now, ammonia, when it is dissolved in water, it weakly produces hydroxide ions. Here's how we would write the reaction for that. So when ammonia reacts with water, ammonia acts as a base, and it accepts a proton from water which donates one. This leaves us with ammonium and hydroxide. Now, because ammonia is a weak base, this reaction is not 100% on the ion side. It's actually going in both directions. So we should use reversibility arrows, the bidirectional arrows showing forward and backward equilibrium. And that's an important distinction. For strong acids, we always will use the forward arrow, but for weak acids and weak bases, we will use the reversibility arrows. All right, so let's go to the next page and we will start talking about pH. So you're likely already at least a little bit familiar with something called the pH scale. The pH scale is a way that we can express the acidity of a solution. The scale basically consists of three main regions. There's the acidic region, which means that there's an excess of the acid form of water, which is H plus ions, or hydronium ions. There's also the alkali portion, or the basic portion, which means there's a deficiency of those H plus ions, or you can think of it as an excess of hydroxide. And then finally, there's the neutral, which is a balance, a perfect balance between hydronium, or H plus, and hydroxide. So those are the three main regions. We can think of this as sort of a scale where it's almost like a balancing act, where if there's a perfect balance, we have a neutral solution. But if there's an excess of proton, it's acidic, and that has a low pH value. And if there's an excess of hydroxide, that means it's a high pH or basic. Now, numerically, the pH scale goes from 1 to 14. And a pH value of exactly 7 is neutral. And anything below 7 is acidic, and anything above 7 is basic. The pH of a solution can be measured in a variety of ways. There are colorimetric indicators. So these are organic compounds, dyes and pigments, and other types of organic molecules that will change their three-dimensional structure, these molecules, based on the concentration of protons or hydroxide ions. And they will change color as a result of their change in three-dimensional shape. And this actually gives us a very nice and convenient way to actually visually see the pH of a solution. Red cabbage is actually an excellent source of something called anthocyanins, which are a molecule that is a perfect example of a pH indicator. Other means we have at our disposal for measuring pH include electrochemical methods. So this is where pH meters come in. These meters are based on, there's an electrode in this device that measures the conductivity of the solution, and from that information, it can be determined what is the concentration of protons, and therefore you can get a precise value for the pH. Now, what we're going to learn about next is where does this numerical information, what is it based on, and where does it come from? And like, what's the deal with 1 through 14? Why isn't it like 1 through 100 or 1 through 10 or something? Why 14? We're going to learn about why that is. It actually has something to do with the chemistry of water, which the pH scale is based on. So let's go check this out in the section, the ion product of water. So in this section, we're going to learn about the numerical basis for the pH scale. And we're going to start with understanding what this P means. Why don't we just call it the H scale? Why do we call it pH or POH? So it turns out that in chemistry, we use this lowercase p right before something to indicate that we are taking the negative logarithm of the concentration of that thing. So for example, when we say pH, what we mean is that the negative logarithm of the concentration of H plus is determined. Likewise, when we say POH, what we mean is that the negative logarithm of the concentration of hydroxide ions was determined. Now you might ask, why do we need to use logarithms to express acidity? Why can't we just directly go to the concentration of the hydronium? And the reason for that has to do with the nature of the way acids and bases behave when they're in solution. And they behave more like a logarithmic curve than a linear curve. And what I mean by that is that small changes in the concentration of hydronium lead to dramatic changes in the actual acidity. Another reason is we use the logarithmic scale because it accommodates the very large range of possible values of concentration. Now, because we're working on the logarithmic scale, a difference in pH of, say, from 4 to pH 5 is that you have 10 times more acidity in pH 4 than in 5. Now, if you go from 3 to 5, 3 is 100 times more acidic than pH 5. And if you go pH 2 to pH 5, it's 1,000 times. That's because we're using the base 10 logarithmic scale. Now, if you need a quick review on the logarithmic scale, just fast forward a bit and go to the next page in the notes. I go over basic logarithmic stuff on the next page. So what we're going to talk about now is where does this pH 1 through 14 come from, the origin of it. So the origin of this has to do with the behavior of water. And it turns out that if you go and you add some acid to water, what you're doing is you're increasing the H plus ions. But you're not just doing that. Actually, it turns out in water, the ratio of protons to hydroxide is always constant, no matter what. So if you're increasing H plus, you have to decrease the hydroxide by exactly the same amount. Likewise, if you increase the hydroxide ion concentration, simultaneously the hydronium ion concentration also has to decrease by the same amount. So it turns out if you multiply the concentration of H plus by the concentration of hydroxide at any pH, at any acidity or any basicity, you will always get the same number. And we call this number the ion product of water, or Kw, and it has a known value. The value of Kw is 1.0 times 10 to the minus 14. So at any given moment, anywhere in the world, if you go and you get some sample of water and you multiplied its proton concentration by its hydroxide concentration, it would be Kw, or 1.0 times 10 to the minus 14. Now, we can kind of see in this, if we know a little bit about logarithms, where the 14 comes from. Because if you take the negative log of 1.0 times 10 to the minus 14, that's the negative log of Kw, you get 14. So what we're going to do now is go to the next page and just do a quick review, a really basic logarithm review. Because most of the logarithm type problems we're going to do in this class can be done actually without the aid of a calculator. There will be some where you need to use a calculator, but for many you can actually just do them by inspection. So let's go to the next page and take a look at that. So in case you need a quick review on the basics of logarithms so that you can do some of this work and understand kind of what you're doing, we're going to go through some simple logarithm issues, and we're not going to get into anything complicated. We basically want to understand what is a logarithm and how do we get one, what does it mean to take a negative logarithm, and then we'll also look a little bit about anti-logarithms here in a few minutes. So basically what a logarithm is, if we say log of x, in English what that translates to is, to what power do I need to raise 10 to get x back? Okay, so if we put in the number 5, right? What power do I need to raise 10 to get 5 back? Or the log of 1,000, that translates as, to what power do I need to raise 10 to get 1,000? Okay, so for 10, the answer is 3. For 5, you'd actually have to do that one on a calculator. Let's answer this question about the few here that do not require a calculator. So log of 100 is, what power do I need to raise 10 to get 100? Well, I'd have to raise it to the second power, so for that one, it's 2. Similarly, for 10, I would need to raise 10 to the first power to get 10 back. The logarithm of 1 is what power do I need to raise 10 to get 1 back? That's actually probably the trickiest one on here, but if you've taken your math prerequisite, that should make sense. And then what about numbers that are smaller than 1? Well, for that we have negative powers. So we would have -1, -2, and -3. So that's your basic idea of the logarithm. To what power do I need to raise 10 to get x back? Now, of course, in math, you might do logarithms in numbers that are not base 10, but we're going to stick to this for pH. It's for base 10 logarithms. So let's put these two concepts together, the concept of pH being the negative logarithm, and the concept of a logarithm being to what power do I need to raise 10 to get some number back. Okay, so let's try that. Let's look at this example. What is the pH of water when the hydronium ion concentration is this 1 × 10 to the -5 molar? So first we need to recall that pH is just the negative logarithm of the hydronium ion concentration. So if we have the hydronium ion concentration, which we're given here, we just need to find the negative logarithm of it. So we're finding the negative log of 10 to the -5. So we need to find out what power do we need to raise 10 to get 10 to the -5. Well, hopefully we can see there that, well, we would need to raise 10 to the -5th power to get 10 to the -5 back. But we are also taking the negative logarithm. So the answer is negative of -5 or 5. And that would be the pH, which is slightly acidic. Let's try another example. What is the pH when the hydronium ion concentration is 1 × 10 to the -2nd power? To find the pH, we need to find the negative logarithm of 10 to the -2. So we write this down. Negative log of 10 to the -2 is what power do we have to raise 10 to get 10 to the -2 back? Well, the answer is -2. And the negative of -2 is 2. So this is also acidic. All right, so let's talk a little bit about significant figures and pH values. Before we begin, just the first thing is I want to fix this. This should actually be 8.0. So let's just change that. All right, so let's say we have a concentration like 1 × 10 to the -8 molar. Now we already understand how to determine the significant figures for a number in scientific notation. For example, we put our insignificant zeros into this -8 exponent of 10, and we leave all the significant digits over here where the 1 is. So that's scientific notation. Now when we convert this number into pH, we use the logarithmic scale. And because we're using the logarithmic scale, that 8 value gets put into the pH, because it's the power of 10, as the first digit. So the 8 will appear there, although that's not a significant digit. So what we have to do is express after that 8 the number of significant digits the number actually had. So in our example here, we have 1 × 10 to the -8 molar, which has one significant figure. We express that in the pH by putting 1 decimal place after the 8 to account for the 1 significant digit. Now, if we had 2 significant figures in our concentration, we would have 2 places after the 8 for those 2 significant figures. So let's take a look at this next example. What is the pH of a solution with hydronium ion concentration of 1.00 × 10 to the -3 molar? So first we notice that there are 3 significant figures in the concentration. Next we have to evaluate the logarithm. To what power do we have to raise 10 to get 10 to the -3 back? Well, we would have to raise it to the -3rd power. And the negative log of -3 is 3. Now that 3 did not come from our significant figures. It came from insignificant zeros. So we have to express our number of significant figures after that 3. And we had 3 significant figures which means that we have to have 3 decimal places after the 3 to account for that. Now, the calculation of the logarithm here gives zeros for those values in those positions after the 3. However, they are important and we need to write them down because, as you know, zeros after a decimal point are always significant. Okay, so that's a good overview of the types of logarithms that we need to deal with pH and as well as significant figures. Let's go to the next page. All right, so now we're going to look at an example where we are sort of reversing the pH process. So in this case, we have a pH and we want to know what the concentration of hydronium is. To do this, we use what's called an anti-logarithm, or sort of undoing or reversing a logarithm. And for pH, we use the anti-logarithm like this. We raise 10 to the negative pH to get the hydronium ion concentration back. So for all types of calculations like this that I'm going to be showing you in this section, you want to keep a list of these going because they're very useful. And this will be kind of the first one that you'll want to have on your sort of master list of pH calculations that are useful. So how do we solve this problem here when we have the pH and we want to know the H+? Well, we raise 10 to that power of 3.200. Now, typing this into your calculator will give you the hydronium ion concentration as 6.31 times 10 to the minus 4, and that's in units of molarity, or moles per liter. All right, now the second part of the question asks, what is the hydroxide ion concentration? So a key concept here is that the ratio of hydronium ion concentration and hydroxide ion concentration is a constant. So if you know one, you can always know the other. So in this example, we can simply divide Kw by the hydronium ion concentration, which we just determined, and that would give us the hydroxide ion concentration, which, based on my calculation, gives 1.6 times 10 to the negative 11th molar. Now let's stop and just double check our significant figures for everything here. So I'll start with the pH to concentration conversion. Notice that the pH shows there are 3 decimal places after the negative 3. So we've got the 200. So that means our concentration had to have 3 significant figures in it. So we have 6.31. And then we take that 6.31 and we divide the Kw by it, and we get a value with 2 significant figures because we're following the rules of division. All right, let's look at another part of calculating with pH, and specifically I want to talk about neutral solutions and what it means for neutrality. Suppose that you had exactly the same concentration of the hydronium and the hydroxide. If we know that they are both equal to each other, we can figure out what each one is independently based on the fact that Kw is a known constant. Because Kw equals the concentration of hydronium times the concentration of hydroxide, if they are both equivalent, it's like saying Kw is equal to the hydronium ion concentration squared, or equivalently, Kw would be equal to the square of the hydroxide ion concentration. So what we're saying is that if the solution is neutral, what that means is that the hydronium and the hydroxide must be equal to each other. There's not more of one than the other. They're exactly equal. And if they're exactly equal, we can find what the value is because we know Kw. And all we have to do is square the hydronium ion concentration or the hydroxide ion concentration and set it equal to Kw, and then figure out what H plus is and what OH minus is. So let's go ahead and do that. So we know that in a neutral solution, the square of the H plus ion concentration is equal to Kw. So then to find H plus, we just take the square root of Kw, which is equal to the square root, of course, of H plus squared, which is just equal to the concentration of H plus. And that will give us the value, which is 1.0 times 10 to the minus 7 molar. And then because we know we are in a neutral solution, we know that hydroxide ion concentration and hydronium ion concentration are equivalent. So we can say that hydroxide is also 1.0 times 10 to the minus 7 molar. And then we can find the pH of the neutral solution by taking the negative logarithm of 1.0 times 10 to the minus 7, which gives us 7. So that's how we can derive what neutral is, being pH 7, and as well as the concentration of 1.0 times 10 to the minus 7, just based on what we know about Kw and the mathematical relationship of logarithms. So let's take a look actually at another useful trick actually for pH calculations. This one's based on the fact that we know that hydronium and hydroxide ion concentrations, when multiplied together, give us this 1.0 times 10 to the minus 14. A useful relationship comes out of this if we take the negative logarithms of both sides. So we take the negative log of the left, so that would be the negative log of H plus times OH minus, and then we also take the negative log of the right, which is the negative log of 1.0 times 10 to the minus 14. Now we know that the negative log of 1.0 times 10 to the minus 14 is just 14. But what's the negative log of this product? Well, the properties of logarithms explain that the logarithm of a product can be expressed as the sum of the logs. When applied to this example, this property of logarithms tells us that the negative logarithm of the product of these two concentrations is equal to the negative logarithm of the concentration of hydronium plus the negative logarithm of the concentration of hydroxide, which again equals 14. Now we already know that the negative log of H plus is also called the pH, and the negative log of OH minus is also called POH. Now why this is useful is that pH plus POH will always equal to 14. Now a quick note about significant figures with this number 14. We know that the hydronium and the hydroxide concentration are exactly equal to each other. And what that means is that 14 has an infinite number of significant figures, so it's unlimited. So that turns out to be a very useful calculation. And while you won't have to derive this, it's a very useful formula or little trick that we use to be able to quickly get at pH or POH when we know the other one. So let's see what I mean on the next page. So in this example, we are being asked for the pH and the POH of a solution with a known hydronium ion concentration. So we have to start somewhere. Probably the easiest place with this is to simply convert the concentration of hydronium into pH. So we find the negative log of 1 times 10 to the minus 8, which turns out to be 8.0. And now we need to find the POH, which we can find pretty easily using that formula I showed on the previous page. So we know that the pH plus the POH is always equal to 14. So now we can find the POH simply by subtracting the pH from 14. And remember that 14 is an exact number, so it has an infinite number of significant figures, and we're subtracting 8.0, which goes out to the tenths place. So when we write down the value of 6, the calculated value, we need to express it to the tenths place as well. Okay, so that wraps up our discussion of Chapter 13 and acids, bases, and the pH scale. Please let me know if you have any questions, and I hope you're doing well. Take care.